Okay, so it's time to let's start. So this is COVID, session 4, and I'm Naoki Masuda from the State University of New York at Buffalo, and I'm sharing this session. So we have 4 talks, so they each, as usual, like says 12 minutes plus 3 minutes of discussion. So the first speaker is Sebastiano Bontorin, and he's gonna share his video, pre-recorded video. So please go ahead.
Oh, here is the video. Now I'm going to start it. Thank you. And later I will be available for questions. Good afternoon. My name is Sebastiano Bontorin, and I am a PhD student at Fondazione Bruno Kessler in Trento. Today I will present a work from our lab with the name Multiscale Statistical Physics of Human SARS-CoV-2 Interactome. The aim of this work is to characterize and find similarities between SARS-CoV-2 and other known viruses. We analyze their virus-host protein-protein interaction networks, and with the idea of eventually exploit existing information about these known viruses to understand more about this new virus. We perform a multi-scale analysis at different scales, microscopic, mesoscopic, and macroscopic, using methods from statistical physics of complex networks. The idea is to use this kind of analysis with the potential for future applications, such as finding possible candidates for drug repurposing. Before speaking more about these methods, a brief overview of this dataset. We have reconstructed these networks, the interactomes, by using information from 2 public repositories, 2 databases, BioGrid and String. We combine this information for reconstructing the human interactome. Information and interaction from viral components were taken from String, and specifically for SARS-CoV-2, these are not present in String. So, but these were experimentally observed and they were published on Nature, and we've taken information from that. So this interactome, virus-host interactome, is actually composed by 2 elements, the human part and the viral components that interact by targeting human proteins. So this multiscale analysis, we start from a microscopic one. We use 2 methods, standard percolation analysis, in which we remove fractional proteins and we find how a statistical property of the system, such as the size of the giant connected component, is affected. And then we use another method, which is the analysis of propagation of a perturbation from a regulatory dynamics, how it impacts the system. Then we analyze the mesoscale structure. We analyze how the fact that viral interactions can alter functional links of targeted proteins. We remove them, and this affects the modular structure, and we see we analyze it for all the viruses. And then we define density matrices that can map network states and information flow in these networks to these macroscopic functions. Namely, we use the Monsieur function and the von Neumann entropy, which are macroscopic functions for the entire system, and we use this to characterize the perturbations introduced by adding the viral components. So starting from the percolation analysis, the idea here is that we use the size of the giant connected component as a proxy for the remaining functional part of the system after the targeting of the virus. As we can see here, we remove a fraction of proteins from the interactomes. We can remove them randomly or based on some specific metric, the betweenness or the degree. And as you can see, all the different virus curves overlap with each other. And this is telling us that a purely topological and structural analysis of the entire virus-host interactome is not giving us the distinguishing features that we are searching between these viruses. If we move to propagation of perturbations, we move this with our regulatory dynamics. The idea is that we start a small perturbation in a node by shifting in the targeted node by the virus. We shift its activity and we track the propagation of this perturbation throughout all the system. We use this as a probe to quantify the impact of the virus on the local topology of the system. what we find is that the impact from single targeted proteins does not depend on the degree, the number of connections they have. So therefore, when we compute the cumulative impact of a single virus, we find that it is proportional to the number of proteins it targets on the human interactome. So, but also this analysis is not able to give us those distinguishing features that we are searching. So we now move to the mesoscopic analysis. As I said, in this case, what we do is that we encode the viral interaction as an alteration of the functional property of the targeting proteins. So therefore, we remove their functional link. And the human protein-protein interaction network is a highly modular system. So after we remove these links, their modular structure can vary a lot. We use two different methods to detect their modular structure before and after the targeting. Specifically, we use a modularity maximization algorithm, a standard Louvain algorithm, and a Bayesian inference method, which is the degree-corrected stochastic block model. We find here are the results for the Louvain algorithm. We find an increase in the number of modules and also a shallower hierarchical organization. And this is telling us that there is this decentralization in the functional organization of the system and a less efficient capability of distribution of information. We also show how we can use information theoretical tools such as variation information and normalized mutual information to quantify the difference between the modular partitions before and after the targeting. So what we find is that even by using two different algorithms that yield a highly different number of modules, we can find that the human SARS-CoV-2 is similar to other human coronaviruses with respect to how different the new partitions are with respect to the older one, which is interesting because all the other coronaviruses do not share targeted proteins with the new SARS-CoV-2, and they also have, in some cases, a very lower number of targeted proteins. But still, they show this high difference in the partition calculated by using variation information or NMI. So moving to macroscopic function. As I said, we can define these density matrices. In this case, we can use a propagator for diffusive dynamics, which is then defined by using a Laplacian matrix. And from this definition of the density matrix, we can define two macroscopic functions that can define the state of the system, which are the Massieu function and the von Neumann entropy. The idea is that we can compute this for the system before adding the interaction with the viral components. Then after adding this interaction, we can recompute them. And by subtracting, we can find the perturbations. And we can compute this for different values of beta and defining the trajectories that you see as a function of beta. So what is the meaning of this parameter? Well, if we go back to the density matrix, we see that in the case of a propagator, beta plays the role of time. So for small beta, we have a small times, which is in analogy for a random walker, which is not able to explore the entire system, so small times. While if we increase the value of beta, the random walker is able to explore a farther region of the system. So therefore, in this way, we can associate the small beta, specifically beta equals to 1 to short scales, while beta equals to 3 to longer scales. And indeed, here are the results. The idea is that after computing these trajectories, we can select these different scales, and this is a multi-resolution approach. And for a given value of beta, we can embed our virus given its value of the perturbed Massieu function and perturbed von Neumann entropy. And we can cluster these viruses on this two-dimensional space. And what we find here is that for beta equals to 1, so short scale, SARS-CoV-2 clusters with other respiratory illnesses such as influenza A and the SARS-CoV, while at longer scales, it clusters with HIV-1 and human T-cell leukemia type 1. So this is telling us that SARS-CoV-2, instead of having simple localized effects, typical specific viruses, instead is a systemic disease with systemic effects. So concluding this work, a brief recap of the results. As I said, percolation analysis is telling us that adding viral components has negligible effects when it comes to structural properties of virus host interactomes, while propagation analysis is not sufficient also to identify distinctive patterns. If we move to mesoscale analysis, which is telling us about the decentralization of functions and less efficiency in information exchange after the impact of viruses with respect to the modular organization. And finally, by using these new macroscopic statistical functions, this is revealing us a different scale of impact for the virus, where at short scales it's similar to other respiratory illnesses, where at larger scales, where there is this interplay between the topology or the information flow, this is more relevant. SARS-CoV-2 instead appears more similar to viruses such as HIV and HTLV-1. So this concludes my presentation, and thank you for your attention.
Yeah, thanks for a great talk, video. So there's time for discussion, so we have plenty of time. So if you have questions, just, unmute yourself or just write a question or raise your hand on the chat. So please go ahead.
Can I ask something?
Sure, so Bossa, go ahead, please.
Sorry. Okay. So just one question. Are these weighted networks, this protein-protein interactions and viruses, are these weighted networks, or how do you treat these weights of the ages?
So we have taken the data from the string and repositories, and we have considered unweighted networks.
Unweighted, right?
Unweighted, we have considered combined scores above a certain value.
Okay, but there are weights, for instance, in the data. Is there enough data to derive some weights of the network?
Well, one could use these confidence and combined scores to estimate some weights. In our case, we decided to just binarize them.
Okay, right. Thank you. Thank you.
Great. Other questions? Let me just ask one first question. So that I want to have a clarification question in the first part. So where you said that the perturbation effect doesn't depend on the node, but say when you perturb, let's say node I, and you looked at the response of say node J, something like this, right? So I think it depends on the dynamics. So they say, did you assume linear dynamics, non-linear dynamics?
This is a specific case in which we have worked with a framework in which we were simulating regulatory dynamics with a Hill function defining interaction between nodes. And we are working in a linear regime. And this specific form of the dynamics, you actually find that there is no dependence on the degree on the amount of cumulative amounts you take the norm of the old system in the perturbed state. This does not depend on the degree of the source node.
I see. Got it. Thanks. So we still have time. So the other questions? Let me ask one more. So you say these are 3 types of analysis. And the last one, you described the last one is a macroscopy, but at the same time, I feel that it's, how can I say, the multi-scale analysis itself, because by modulating the value of B, you could go from, say, local, relatively local to global, right? So is it ever possible to, say, try to produce the second result, which is from the same mesoscopic analysis by the third analysis by, the choosing the intermediate values of beta,
Yeah, this is a very interesting question, actually. And I think that it will be interesting to actually do this. And in the third analysis, we do the perturbation by adding the viral components, and then we compute these new macroscopic functions. It is actually interesting if we remove the targeted proteins, as we did in the second analysis, the mesoscopic analysis, and then we compute those macroscopic functions.
Oh, I see.
And it might be interesting if we find the same results with this approach.
Might be interesting. Yeah.
This is a good idea. Thank you.
Thank you. So the time is up. So let's thank the speaker, Sebastiano. Well, virtually. And let's go to the next talk. Thank you very much. Okay, our next speaker is Giorgios Barmparis.
Perfect. Thank you very much, Mr. Chairman.
So do you want to share your screen or how do you want to proceed?
Yes, I'm going to share my screen.
Yes, please go ahead.
Okay. Can you see my talk?
Great.
Okay, great. Thank you. So today I will talk to you about physics-informed neural networks and how we can use them in order to predict the COVID-19 pandemic. This is a work I've done with Professor Tsironis here in the Department of Physics in the University of Crete in Greece. Firstly, the first topic the first thing we started with in our research was that we saw that China had reported some daily cases about the COVID evolution in their country, and we realized that this looks like a Gaussian function, and we did the hypothesis that we can predict, we can use the Gaussian function in order to fit the data we have from the pandemic. At that time, a lot of other people, other groups used this hypothesis and started fitting the daily cases using a Gaussian function, but we didn't have any indication why a Gaussian can be a good function for this case. And then we realized that we can have some justification about the Gaussian function, and this is when we, at that time, the very first time of the pandemic, almost all the countries started with imposing some measures, social distancing measures to their people in order to gain some time and realize what's going on and how they will do with the pandemic. So we realized that if we have a time-dependent infection rate, these are the equations for the SIR model, the very basic epidemiological model that we use. Susceptibles, infectious, and removed or recovered, hopefully. This is, if we generally use time-independent infection rate, that it is A, and removal rate, that it is mu. So we realize that if we have this time-independent, without measures, time-independent infection rate, then the evolution goes as we really know with the SIR model. And here you see the black dashed line is the Gaussian fit on these data. But if we introduce a time-dependent infection rate, and especially an infection rate that gradually drops as it is more efficient, more usually we do with taking measures from the governments, we gradually decrease the infection rate, we realize that we can go to the infection can get a much more closer similarity with the Gaussian function. And we used also the Pearson correlation coefficient. For those that are not familiar with this coefficient, if the Pearson correlation coefficient is -1, then we talk about a perfectly anti-correlated curves. If it is equal to 0, we have non-correlated curves. And if it is equal to 1, then we have a perfectly correlated curves. So you see here that if we don't have time-dependent infection rate, then the correlation coefficient, the Pearson correlation coefficient is 0.964. But if we introduce some kind of time-dependent infection rate, and especially this gradually decrease of the infection rate, we have a correlation coefficient that goes much closer to 1 and indicates that this is what, that the Gaussian function is much closer to the infectious time-dependent function. So this was the first part of our work, and we use this Gaussian function in order to predict the infection evolution in 8 countries, Greece, and the Netherlands, and some others. And with the Gaussian, we were lucky that we could estimate also the peak of the infection and also the horizon of the infection. So this was the first job we did. We tried to say that countries that are going to impose measures, and especially gradually measures, then their infection evolution will look like a Gaussian function. And if we fit the Gaussians, we can estimate the peak of the evolution, the peak of the infection, and the horizon of the infection. And this is the peak and the horizon predictions we had at that time. This is early April of 2020 for these 8 countries. In case of Greece, that it appeared to be that we had a lot of measures. The model was working pretty good. So in cases like the United States, our model was not working well because they didn't actually impose any measures. Actually, the effectiveness of the measures that they took was not that good. So the idea is that in order to predict the infections, we need a time-dependent infection rates. And this is how we decided to introduce physics and artificial intelligence in this problem. So we started with the SIR model, but at this time we use that the infection rate is a time-dependent variable. And we introduce a new variable, this Q of t, that we write the infection as e to the Q of t minus nu, where nu is related to the removal rate. And then we can obtain this nonlinear differential equation that is exactly similar to I of t in this SIR model. So what we gain by doing this introduction is that we have a new equation that we can solve this equation and get the infection for the pandemic without having to know what's going on with the susceptibles and all the other parts of the that take place in this system. So we did this mathematics, and then we decided that we are going to use an infection rate that is sigma 0 plus sigma t, so it's a linear function, and the constant mu, which seems to be a good approximation. So in order to write this problem using artificial intelligence is that we introduce an extra term in the loss function. This is what we call physics-informed neural networks. Neural networks that they do not just know to minimize the predictions around the data, mean square error of the data, the real values minus the predicted values, but they also have an extra term that have to minimize, that it is a term that has to obey some equations. In this case, the infection has to obey the SIR model. And this is that this the loss function now, we add this equation actually, that it is similar to the one that we have here, just we have replaced Q with X. So we have this removal rate also there. And the idea is that we are going to train a model that will minimize the data for each one of the countries. And also the model should have knowledge about the function that it should obey. It should obey some functions like the SIR model. And here we have an extra parameter that it is the A of t, the infection rate, and the removal rate. So the model has to find the best parameters A of t and mu, so that it can go closer to the SIR model. So this is the flowchart of our model. We create a model as usual, that it is data-driven plus physics for neural network, which means that we have an extra term in the loss function there. We started training the model using simulated SIR data, and this is just to accelerate the training for the model in the future. So we have a model that knows how to solve the SIR model, a machine learning model that knows to solve the SIR model, sorry. Then we load the data for each one of the countries and the pre-trained model, which moves the data using a 7x steps. It's a weak moving average. And we train our model to those specific data for each country using early stopping. And then we are able to extract what is the best A of t and mu for that country in order their data to obey also this SIR model. We solved then the SIR model using the extracted features we had from the machine learning model, A of t and mu. And then we use the initial conditions as fitting parameters of the evolution of pandemic to each country in order to fit the data of each country. Finally, if there are any other countries, we start again and so on. So by using the model, we were able to extract the features. We were able to understand how efficient were the measures for each one of the countries and how we can see the measures in the countries. So you see here for the United States, for example, you see that A of t is this black dashed line here. It is almost constant, which means that they didn't impose a lot of measures, or at least the people in the United States didn't actually use any of those measures. So also we have some extra variables here that we increase or decrease the infection rates by 10% in order to see how the pandemic would evolve in this country if they had more efficient or less efficient measures. And we see again that in case of Greece, we have the slopes here, the infection rate. It seems that it is the more negative slope here, which means that Greece had the more efficient measures among the countries that we are interested in. So then we plot here the minus the slope for the measures. And you see again that in the case of the United States, this is almost zero. There's no slope. It's a constant A of t, but in Greece, we had a lot of efficient measures. And this is for the first wave. For the second wave, actually, we did also some predictions, and this is the second wave. So we use our model, and by assuming that the infection rate is not going to change a lot for the next week, we do what we call short-term predictions. So we use our model, and here you see some predictions about the next week in each country. And the test data in purple circles there, which means that we are close, if we can say, to the predictions we have. The most importantly, in the case of Greece, where we are more interested in, we are continuing doing predictions every Friday. And this is how the evolution of the infection has gone in Greece. The green dots are the reported data. And here again, we have a second lockdown in Greece on November the 7th. And you see here for the first part, you see that the infection goes, our model predicts more or less very good numbers, but then after the infection, and let me show you the zoom here, you see that after the lockdown, the model predicts a lot, it overestimates the predictions. And this is because it assumes that the infection rate that we had the previous week is going to be the same also the next week. But due to the lockdown measures, the infection rate is very, has changed a lot, and actually it has decreased. And we have here also another point that it is very interesting, that we had a rapid increase in the infection rate. And also again, here we see that the model does not realize what's going on. It predicts that the evolution will go at 500 cases per day for the week of October 19th. But we see that it starts growing in Greece, and then the model is able again to catch up with infection in our days. Today, this is the circle for today. It's about 1,500. Before a few minutes, the Greek national, the National Public Health Organization reported 1,382 cases, which means that the model is again doing well predictions, and it seems that the infection rate is stabilized again. I'm done, Mr. Chairman. Thank you for your time.
Great, thanks for a great talk. So we still have 2 to 3 minutes. So okay, there is a question in chat. So let me just read, or you can speak.
Sure.
Let me just read first. Do you have these predictions online, which you do every
yes, actually here, but this is unfortunately, this is for our Greek speakers only. This is the prediction. This is announced before a week, if I remember well.
Mm-hmm.
Unfortunately, only for the Greek speakers. We are working on adding this in one of our new publications.
Great, thanks. Other questions?
Can I have?
Yes, please.
Yeah.
When you have this kind of expression for this is fluctuations of daily cases, right?
Yes.
How do you express the total, the infectious curve? Do you have a, this is well known in the SIR model. logistic curve will come, you know.
Yes,
Especially
this is
when you have this lockdown, it will level up and you have this kind of 4 parameters for logistic curve. But if you have this expression, which is Gaussian, then what's your expression for the total number of infections?
it's an error. It's like an error function.
Aha, okay.
So
So
the logistic,
is it more correct? Is it more correct than logistic?
the Gaussian is correct if you have measures. If it is a freely involving pandemic, then without measures, then the Gaussian is not a correct function to use.
Okay.
But if there are measures that affect the infection rate of the pandemic, then you have a Gaussian, and then you conclude to an error function. The logistic function goes to an error function.
Okay. Interesting.
Thank you.
Thanks.
Okay, if there is any short question, we have still time. Okay, otherwise it's almost time, so let's thank the speaker again to go to the next talk. Thank you very much. Okay, we have two more talks, and the third speaker is Francisco Paletta. Start here. All right, good. Yeah, share screen and say start whenever you can. Yeah, please go ahead if you're ready.
Can you help me with my camera? Okay, sorry.
Yeah, it looks good. Looks
A
good.
little trouble here.
Yeah.
Good afternoon to everybody. Thank you very much for being here. It's a pleasure. My study here is how to use the data web information retrieval in order to help using infographics in the COVID-19 pandemic. So, I'm from University of São Paulo, and my study is, we are doing this study together with University of Carlos III in Madrid and University of Porto in Portugal. This is the areas that I have been studying here in Brazil: the complex system design and management, information knowledge management, information retrieval, digital library, digital humanities, and data science and analytics. The study has the objective of try to understand the role of the infographics can play in order to help to educate, to create educational campaigns, to educate our community here. In Brazil, we have a continental size, and also our population, the total population is 220 million. So it's a very high population, very complex to control. So the study has the objective to collect information from all over the world in order to produce infographics that can help the education of our population. So we have two things here to consider. The information retrieval is in one side, and the linked open data to creating knowledge towards the pandemic issue. So this is the architecture of the linked data applications that we have been using here to build these linked data applications that can collect information from every website that will help us to use the infographic as a powerful tool for education. So this is one example, for example, where we have been collecting data. And one problem when we are using infographics to develop an educational campaign is that we have the phenomenon of the fake news. And we have been using some websites in order to retrieve data from these websites and to avoid that the fake news would create a bad situation for our population as far as the information concerned the COVID is in base. The results of what we have been doing here is to analyze what is going on all over the world, putting together the information that can help the construction of the infographics that we have been using in every kind of organizations here in Brazil, like a public organization or government organization. So the idea is to use the information that I have been producing all over the world in order to create a database that will help us in our educational campaign. So we are collecting data on the daily basis, and this data, we have been analyzing this data in order to put together the information that we consider essential and structural for our population, entire population. We have to consider Brazil has a continental size. It's very complex. So it's different when we are talking about, for example, Greece or Portugal or even though Spain or France. The continental size of Brazil produce a lot of issues and problems as far as the information flow are concerned. So we have to take care how to manage the information and to avoid that the population will not taking care of their responsibilities to avoid the contamination. So this data we are collecting from everywhere. For example, here where we trying to explain to the population how we have the contamination, how was the process of the virus contamination, using infograph as a powerful tool. So it's very simple language that can help the entire population to understand the risks that they are applying when we are considering the infection process. For example, here nowadays we have a tremendous problem here in Brazil regarding the vaccine. So if the population will accept or not the power of the vaccine and what will be the source of the vaccine. So the idea of using infograph, again, as a powerful tool to help us to create and to build educational process, orientation process, talking in one language that the population will be able to understand and to make their decision regarding the vaccine process and how the vaccine can protect the immunization process. Another thing that is important in this project that we are facing now, for example, to explain why we were able to develop one vaccine in almost 1 year, in less than 1 year, when the last one took 4 years to develop, is the amount of money that we have in this process. For example, if we take a look in this graph, you see in 2020, most of 95% of all the spending in this area was in this year, and this is why this amount of money was helping the world to develop the vaccine. Again, this is some numbers that we are discussing with our training and educational process to show how Brazil are dealing with this process and how dangerous is the situation in our country, because if we don't have the help of the population, Brazil will continue to face a lot of trouble together with the United States. So this is some examples that what we have been doing. So we are putting all this information in local language in Portuguese. So, but we are using the World Health Organization infographics in order to put the information in Portuguese that will help the educational process, even though the private organizations and public organizations. another issue that we consider very important to explain and to avoid fake news is to use infographics in basic things, how to wash fruits and vegetables, how to get grocery shops safely, how to avoid shaking hands because the new coronavirus. So it's a very simple strategy that is helping the country to overcome the issues that we have here as far as communication is concerned. Again, so basic things regarding how to do with your laundry clothes, how to the information regarding if you should use gloves or not, how to deal with banknotes and coins is very basic things that we are using the data web information retrieval and the complex system linked data in order to get from the right source the best information available, to translate this information in local language in order to help one country with 220 million people to face the issues regarding the COVID-19. This is it. This is the project. This is this is what we have been doing here in this project. Thank you very much.
Thanks for your presentation. So we have some more time than others. So we have 5 minutes. So are there any questions from the audience? Let me just start myself. So what is special about infographics? I mean, as compared to other, let's say, databases, I mean, what is the particular strength of the infographics platform?
Well, we have several databases, but when you consider the country reality, it's very complex because people, most of our population, they don't have access to internet. So, for example, if you go to Amazon, if you go to the very north of the country, we have Indian population. So we have to take care of these people, and we decide to use infographic as a simple language. So we use different databases in my university, in my research center, we are collecting this information for the worldwide database, putting infographics in a simple language that will fit our reality as the entire country. So we have some very advanced areas where this is not a problem, but when you consider the Brazilian, our country dimensions and the poverty that we have here, we have to do something regarding the education if we want the population cooperation in order to avoid the mass infection.
So does this imply that the USA platform may have, let's say, potentials in other countries which are in an economic, let's say, difficulty, like in many African countries, or you're focusing only on, say, Brazil? Or?
We are collecting, the source of information is worldwide. But in this moment, we are doing this for Brazil, but the idea here is to spread throughout the Portuguese language speakers in Africa and mostly in Africa. All the countries that speak Portuguese, they can take advantage of this job, this research here, in order to help the other countries to use the same strategy for the education in this process. And we are facing, for us, it's clear that we have more 6 months to deal with this issue, at least in our country. So,
thank you very much.
Thank you very much.
Yeah. Are there any other questions from the audience? We still have time, like 3 minutes, 2 minutes, 3 minutes. Okay, so here's a question. So how you, let me just read because it's on the chat. So let me just read for the audience. So how you attempted at explaining the complex concept of direct reciprocity, mask wearing. You can also read it.
Yeah, the idea when we are talking with the mass population, we are trying to avoid any mass language. This is why we are using infographics. If you use infographics, you can transform the complexity of this situation in a simple language that a normal, simple people can understand. You know, my grandmother with 75 years old, she can understand. And even though if we are talking with our Indian population or the people that live in the poverty, in the slums and situation that the support and the medical infrastructure is not there. The country complexity is very, very huge. And we have to use a simple language. And this is why we are using this strategy, collecting data from all the databases.
I think the question is more about, say, they say direct reciprocity. I mean, mask wearing is direct reciprocity. Right? So if you wear a mask and you make the other party safe and vice versa. So it's simple, but it's a complex concept. So that's where question is at, I believe. If not, please correct.
Okay.
So if you have any particular comments on this question regarding this particular, the direct reciprocity of mask wearing things.
Yeah, this is one thing that we have to think about. We didn't think about this question. We will consider this in the near future.
Okay, good. Thank you very much. Our time is up. So let's thank the speaker.
Thank you.
Okay, so let's move on to the last talk, which is by Marta Gonzalez. Are you speaking yourself? Yes, seems to be so. Okay, Marta, floor is yours.
Hello, can you hear me well?
Yes, very well.
Okay, I recorded my presentation. Can you see the screen?
Yes.
Okay, hopefully the sound is well. You let me know if not, I give it.
Pleasure to be here to talk to you about COVID-19 and the role of mobility and the urban form. As you know, all over the planet, we have been tracking for different geographic units, how much our number of cases increased and how they stabilize. And it has been an amazing global effort worldwide. In this study, I want to concentrate in how the R0 or the evolution of the number of cases with time changes according to the mobility and the urban form under consideration. The R0 is a very delicate quantity, meaning that is the changing a little bit in 0.1 in this example. If they are not changed from 105 to 115, and we had 21,000 cases as we had in early March worldwide, 61 days later, we would have 400,000 cases versus 105 million cases. So what control they are not is the exposure, depending how we move, and the infectivity. That it has to do what is the probability that if someone is exposed to somebody, the infection is going to transmit. Then the mask and the lack of the mobility, the lockdown change they are not. What we're interested is in learning, in predicting they are not with a previous case that has been very much studied because we have a lot of data and it's a seasonal effect that is the influenza. We get inspiration of our method by the master, Brian Grenfell from Princeton. And what Brian was doing is trying to predict the influenza infectivity based on, trying to explain influenza infectivity based on a relative humidity, population, and population density. To tell you an example, if you have a more peaky number of infected, more concentrated in time, the epidemic intensity is higher versus more flattened like in Miami. Miami and Atlanta have a similar population and they have different climates. That's why they suffer the seasonal influenza in a different way. Atlanta is more seasonal because the winter you notice it more. Then how they generalize this, they divided the R0 in two terms. One is the base transmission potential per city that depended on the population and crowding. The crowding is the average population per census block square the standard deviation divided by the average minus 1. Then it means the more hot spot of high dense places you have, the more crowding you have in your city. And the second term depends on the time that changes the relative humidity, how it changes with time. Then they show that applying a generalized linear model with these two terms, one that has population and crowding, and the other that has relative humidity, they got a much better Kiki index and a Pearson correlation coefficient of 0.93. Then we got very intrigued and inspired by this aspect of treating the base transmission potential per city to make our comparative analysis and exploring this aspect, going beyond the population density and including the mobility. So I'm going to be showing all the cities I could find mobile data from to measure first the urban form and the mobility, and then exploring these new metrics derived from mobility and epidemic, from mobility and population density, to then go into the COVID-19 R0 prediction. The standard quantity we use to model the mobility is the RG. Instead of working with the usual center of mass, we define the center of mass as the home, because we're talking about the mobility from home. Then we do RCM is going to be the location of the home, and the rest is the weighted visits as usually go from everybody else. Then the RG gives you the radius within which around from home your user is most likely to be found. We average 21 cities, and we see this is a typical curve of RG, which this means that the RG doesn't grow so much with the city in itself. It's more like a scheduled situation. So people have a limited amount of time in the day. We all have the same amount of time, and then the RG has most of the population is found within RG of 5 kilometers from their houses, and a very few ones are with RG more than 40 also. Then, the first thing we explore how the RG distribution depends on the socioeconomic group we are under consideration. And here the story is, depending what matters the most is the socioeconomic segregation. We can have that the richest population here, pink, in LA, live in the in the suburbs outside from the city center, and we have the, in this case, Latin poorer population in LA live near downtown. While in Bogota, here we have downtown, and the richer population live not too far away, as opposed to the suburbs. And then here we have the poorest sectors is the green that live very far away from downtown. So after all, what matters is how far you live from the central business district of the city. And we would be measuring this, grouping the population by how far they live from the city center. And we have, for example, Boston, we have the PRG changes depending how far you live for the different groups, but that doesn't happen in LA. Then we have Wuhan or Shenzhen, in which we have a behavior in between. So why is that? What is going on in here? What is going on is that in Boston, we have one CBD, and in LA is a spread. So Boston is monocentric and LA is polycentric. Then we have the hypothesis is that we can measure monocentricity and polycentricity until now measure only with population distribution, with the RG and the changes of PRG, and we can measure dispersion compact with the population density. For example, we have cities, two monocentric cities, Wuhan versus Boston, but one is much more compact and the other is more spread. One thing is the policy of how dense are our constructions, and the other is how we move. Then here we have our textbook cases. We have the KS, depending on the distance from the city center. We have Boston, it increases, in LA is flat. And then what is going to matter is the delta KS. This delta KS with the distance relative from the city center tell us, it's a new quantity to tell us if it's large, is monocentric, if it's small, is polycentric to the left. And in the y-axis, we can use the crowding or the Gini, only for the population distribution. With these two metrics at hand, we are now going to study cities and how we can predict with a GLM, like Brian Grenfell style, based on the KS and these new metrics that contain both mobility and population. Then we have from Johns Hopkins University, the cases, and with this epi-forecast, they are not using their algorithms to see the slope of changes of the curve. And then what we see is this delta KS tells me something about the different function of the city. For example, we have Bilbao versus La Coruña being much more non-centric than Bilbao. And we have, if we do this KS, the changes of the PRG respect to everybody staying at home is another way to measure the changes in mobility. Then we have that our changes of PRG versus everybody staying at home was much higher after the lockdown. Notice that we are measuring only from February to end of April. That is what we have at the time. And here it comes. First, when we try to predict only for population and the 11 cities in Spain, we see that we have an R0 of 0.40. If we introduce well-known quantities of this population, average RG before the lockdown, we get to 0.74. However, we get a very good prediction with this delta KS and the KS from home-based trips before the lockdown. 0.97, 0.94 with a AIC that decreases. So we add different parameters and we are showing that these are better prediction with the GLM, generalized linear model. Then the other cases are after the lockdown, doing a running average of every 7 days. Then we have a prediction of 0.84 with the combination of population, KS, delta KS, averaging every 7 days. Then to conclude, we have offered you metrics that combine the urban form and mobility, and they are very predictors of spreading dynamics and population crowding and mobility alone. Future work includes looking into the economic sectors and seeing their vulnerabilities to the infections due to purely economic reasons. And currently, we are testing the modeling framework after the European summer, again for Spain that entered in the second wave of infection. And with that, I like to open the time for questions. Thank you very much.
Thank you, Marta. So yeah, it's open to questions. So are there any questions from audience?
Hi, I'm not used to this recording things. I was capturing my own typos while I spoke.
Yeah, thanks for doing that. Right, I'm reading that. So let me start myself. So you mentioned it in this conclusion, but it's a bit, I mean, how can I say, strange question might be, but do you say the picture of how can I say, for example, Boston has the center and some, how can I say, the mobility, I mean, features has some geographic, I mean, relationship from how far from the center, right? So is it predictable from the other measures without using mobility data such as economic status or the distribution, for example, income in region within Boston, or is it really necessary to use the mobility data?
Well, as you know, the lockdown is critical. No mobility, no spread. So definitely the mobility is more than the socioeconomic indicator for sure. Here is about different ways to measure mobility. And then we have a prediction of mobility with population only. You know, everything correlates with population, mobility with population, crowding, and still we get 0.3 better Pearson due to the mixing. That means polycentric, monocentric is different pattern of spreading, if you think about it. This GLM tells you what factors matter. It's not so mechanistic, but it's one way to put an order. And I also, the dream is that we would not be in the United States, my second slide, not having the map of the entire state. It should be by urban aggregation. And that is in that direction, so that we need to find the containers that we are moving together to properly report these cases. It's not the same Los Angeles and San Francisco than Berkeley, so on and so forth.
Okay, thank you.
Ah, nice. I have a question
Yes,
from Juan Rocha.
Yeah, several.
Ah, I didn't see them.
Yes,
Well,
yeah.
you let me know which one I take.
I mean, I think that it's fair to take the first one first.
Yes, I agree. Then I see Lorenzo Righetto. Can you recap? Is most resistant to the epidemic.
So you can recap.
As usual, it's not just a correlation. It's depending on how it changed from the city center. Yes. The way to inform not the post-pandemic is you can do a scenario analysis such that you can see if the mobility start changing, how they are not is going to be changing. There is not a correlation with the urban form per se. Sorry about that. So it's the mix between the KIAS and the RG, right? If we have a monocentric and people move a lot, I cannot tell you that polycentric get more infected. Unfortunately, it's a change. But polycentric cities got higher or not before the lockdown, which is then what Lorenzo is asking. But yes, it's in these GLM models, it's not nice, clear one factor correlation. The cultural differences, excellent questions. Yes, we can conclude the cultural difference have to do if they respect the norms or not. I didn't have Singapore in my data set, but I have, for example, Wuhan, where the epidemic started. The cultural differences are not taken into account here, but the mobility before and after the spreading. Yes, Juan, we are about to submit. We would like to have the second wave because it was too good to be true, you know, Pearson correlation of 0.8 in such a delicate topic. I prefer myself to wait than putting my paper out there in the craziness. And then it came the second wave. Right now we're measuring during the second wave. We did until April. We are doing until September to give us more sobering results, and also to try to understand better certain differences. Like, for example, the one that was asked before. Tell me the story clearer. We're applying a computer science method, and I'm taking it slow, but I want to submit by the end of the year. The granularity is every day. So I have data, it's, you know, phone data. Every time the person makes a call, we have hourly, we detect home with at least 1 day. The minimum amount of time we use was 3 months for all other cities. Notice that for Spain, we could do every day for months, but for other cities, we only measure the urban form. We were working more in a paper of mobility and urban form, and then the COVID hit. And we decided to test things in Spain because we saw the RG changing like crazy. So the paper became, as perhaps happened to some of you, a COVID paper without planning for it. Yes, and if you're working with people moving in cities and the COVID is hitting, you need to, you know, it was tempting to check what was going on.
Okay, so we are exhausting time. So thanks for answering those questions. And thanks, Marta, again for the, and also
thank you, everybody. Nice to see you virtually.
Yeah, great. So thanks for
and
joining.
See you in the urban systems workshop Wednesday and Thursday.
Okay, great. Okay, so thanks for joining all the participants and speakers, and enjoy the rest of the day. Thank you for coming.
Bye-bye.
Yeah.
Bye-bye.
Bye.
Bye. See you.
See you.